Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Senpai. Welcome back, everyone. Today we're jumping into an 11th grade topic, basic trig identities. Now, if you're new to my channel, I'll be putting timecodes in this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what you see today, or even your own homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Senpai and tell me all about it there. At the end of this video, I'll be linking my 11th grade playlist, in which I cover a lot more topics, so if you're interested in that, make sure you stay tuned. This video will have 3 parts, so leave a like, smash subscribe, and let's get started. So in today's video, we'll be covering our basic trig identities. Now I broke this up into 3 parts, the first part being your basic of basics, your second part being your Pythagorean identities, and your third part being what I would like to call your even-odd identities. Now we're not going to spend much time in the basic of basic ones because we've covered this a bunch of times in some other videos that you can find right up here. But I will go over them briefly today just so we can have them all in one place. So for your basic identities, you're going to be starting with your sine and your cosine. So you have your sine of theta and you have your cosine of theta. Now we know that you get something special when you divide the two, right? So sine over cosine is going to be what? We've talked about this. This is tangent of theta. This is our first identity. Now we also know that if you find some reciprocals, if you go a little step further, you can get some more identities. Now we know that 1 over sine is going to be our cosecant of theta. And we know that 1 over cosine is going to be our secant of theta. And we also know that 1 over this tangent here, 1 over tangent, is going to be our cotangent theta. These are some more basic identities that we get from finding reciprocals of our earlier trig functions. And because sine is a reciprocal of cosecant, we know that sine is going to be 1 over cosecant too, right? If sine is a reciprocal of cosecant, cosecant is the reciprocal of sine. So this is another basic trig identity. And you can do the same thing for cosine, which is going to be 1 over secant theta. And of course, you do the same thing here, which is going to be 1 over cotangent theta. So these are going to be our basic trig identities. And once again, if you need some more time to digest all of this, and this is going entirely too fast, check out my earlier videos. Once again, they're up there. You can check them out at any time, but I didn't want to spend too much time since you may have already seen this if you've been watching my videos. So let's move on to something potentially new, our Pythagorean identities. Now you may have already guessed, Pythagorean identities has something to do with the Pythagorean theorem. So let's start there. We have our right triangle. And we have a side A, we have side B, and side C. Our Pythagorean theorem tells us that if we have A squared plus our B squared, we're going to get side C squared. But this is not just about Pythagorean theorem. We have our trig function, so we're going to need our unit circle here as well. And because this is a unit circle, we know that the maximum that you're ever going to get is this 1 here, right? The 1, you're going to go a height of 1, you're going to go out of 1, and everywhere here, your radius for this circle is going to be 1. And we also talked about what the x and y coordinates of these points correspond to. Remember, I've been saying this, if x comes before y in the alphabet, and c comes before s in the alphabet, then our point x before y is going to be correlated to our point c before s. We know this to be true, thus our first part is going to be our cosine of some theta, and our second part of the point is going to be sine of some theta. A nice easy way of remembering the order in which your trig functions are going to correlate with these x and y coordinates. So in this case, this 1 corresponds to cosine, this 0 corresponds to sine, and this 0 corresponds to cosine, and 1 corresponds to sine. And because we know this to be true for some points, we know it's true for all points on this unit circle. That means that any point that you put on this unit circle is going to have a cosine theta corresponding to that very first coordinate, and our sine theta corresponding to the second coordinate. So let's say we have some random point in our first quadrant here, and this is A, B. Our point AB, some random point on the unit circle AB. we know that because A is in our x coordinate, A is going to have to be this cosine of some theta. And we know that B is going to have to be sine of some theta. Now it's going to be the same theta in this case. But let's go a step further and make a right triangle from this point to the x-axis and the origin. So we have something like this happening here. Now this is going to be our right triangle. And this is going to be our theta that corresponds to this cosine and sine here. Now we said this A is going to be how far we're going on the x-axis, so that A is going to go right here, and B was the y-axis, so the B is going to go right here. And we already talked that this is a unit circle. So the radius of this circle is always going to be 1, so the hypotenuse is always going to be 1 for each of these right triangles you can draw here. Now something special happens when we combine these two ideas. We have Pythagorean theorem. A squared plus B squared equals C squared. And now we have this random right triangle which fits this criteria, and we have an A, we have a B, and we have a hypotenuse, right? So what happens if we do all of this and put it together? Well, we have A squared plus B squared equals 1 squared. And we know that 1 squared is just going to be 1, right? So we have A squared plus B squared equals 1 squared, or just 1. Now you may be asking, why are we doing all of this? Where is the trig? Well, here's where the trig comes into play. We already said that A equals cosine theta and B equals sine theta. So if we're doing A squared plus B squared, well, this A squared is going to be cosine squared theta. This B squared is going to be sine squared theta. And that's always going to equal 1 in our unit circle. This is what we call the Pythagorean identity, or one of 3 Pythagorean identities. This happens when you combine your Pythagorean theorem with your unit circle. You get this Pythagorean identity. Now this is a very important Pythagorean identity. There are 2 more, like I just said, but those are a little less important. You don't need to remember those necessarily. You can always create them, and I'll show you how you can create them, but you need to remember this one. It's used so often and will become way more helpful as you continue in your math classes. But let me show you how you can create the other 2 as long as you remember this one here. So I'm going to put them side by side so you can see just how simple it is to create the other 2. We're going to start with the one that we have to remember, and we're going to do something a little different for each one, which is going to result in a new identity for each of these 2 parts. So for this one, we're going to divide everything by sine squared. So everything, top and bottom here, we have sine squared here, and we have sine squared here. Everything by sine squared. This one, we're going to do everything by cosine. So divide everything by our cosine squared. Cosine squared and cosine squared. Now we're going to use the basic identities that we talked about in the first part to see what happens when we consolidate this. Now sine squared over sine squared is going to be 1. Cosine squared over sine squared. Well, if you remove the squares, you have cosine over sine, which we know to be cotangent. Put the squares back in, you get cotangent squared. So this is plus cotangent squared theta, and 1 over sine squared. Well, if you remove the squared, you have 1 over sine, which we know to be cosecant, yeah, and we have the squared back, which is going to be cosecant squared. So this is going to be cosecant squared. Now on this side, we're going to use the same type of logic using our basic identities. So we have our tangent squared, right? We're going to have our tangent squared. We have cosine squared over cosine squared. Same thing, you get over itself, going to get 1. And we have 1 over cosine squared. So this is going to be secant squared. So using our basic identities, we can find the other 2 Pythagorean identities. But like I just said, these are going to be a little less important than the first one. So you don't need to commit these to memory. But as long as you get that first one, you can create these if you need them. All 3 of these together are what we call the Pythagorean identities. So let's move on to our last and final section, our even odd identities. So in this last section, we're going to take what we know about the graphs of our sine, cosine, and our tangent functions. And we're going to get some identities based off of what we know from those graphs. Now we're going to start with a cosine because it's the odd one out, and you'll see what I mean by that. So if we were to start with cosine of some theta, it will look something like this. Now, it's not going to be perfect, but you got the idea, a rough sketch of what cosine looks like. But what do you notice about the behavior of this graph if we're focusing on this y-axis here? This side looks like this side, right? If you were to go, let's say, A, and intersect the graph here, and then go negative A, right? You would get, well, this is not exactly even, but once again, you get what I'm talking about here. You would get the same value, whatever that value is here, right? Likewise, if you were to go B and go down to this, and you would go over here to negative B and go down, this would be the same exact value as well. This is because cosine is going to be an even function because it's symmetric across the y-axis. So the value you get at A is going to be the same value you get at negative A. The value you get at B is going to be the same value you get at negative B, which leads us to our even identity. Cosine of some x, whatever that x is going to be the same as cosine of that negative x. Whether it's this A or negative A, you're going to have the same value. B or negative B, you're going to have the same value. Cosine of x is going to equal cosine of negative x. That's our first even odd identity. Here we have a rough sketch of what sine looks like. Now, this is not even. You can tell just by looking at it, it's not like cosine, it's not an even function. In fact, this is what we would call an odd function. Now, it has the property, if you go to A, right, and you go up, and you go to negative A, well, clearly it's not the same value. But if you go down, it's going to be the negative of that value, right? Go A, you get this positive value here. You go down here, you're going to get this negative of whatever that value is. If you were to keep going to B, and you go down, now you got some negative value, but if you keep going to B, and you go up, this is now positive. So it seems like we're opposites, at least sign-wise, we're opposites, which lets us know that this odd function that's symmetric across the origin is going to be leading us to this identity. Sine of some negative x is going to be the same as negative sine of x. Take a look at this. If we do sine of this negative a here, and let's say this was negative 1, right? Well, if we were to do sine of a, we would get a positive 1. Well, if we put that negative up front, we now see that the same exact value here. Sine of negative x is going to be this negative sine of x. And this is an odd function. Different behaviors for even and odd. You can try it out with more values and you'll see that this is always going to be true. Now, if we look at tangent, we see, once again, this is not an even function. This looks more akin to our odd function that we just talked about, our sine, right? Well, not exactly like sine, but it has the same type of properties as if you go to a here and go to negative a here, you're not going to get the same exact value, but you're going to get something that's opposite sign-wise. So the value, the absolute value will be the same, but this sign makes it the opposite. So this is another odd function, which lets us know that our identity is going to be very similar to our sine. So if we have tangent of some negative x, we're going to have a negative tangent of that same x. And of course, you know that this keeps repeating as you get across the different asymptotes. But we're just going to focus on this part right here because it's the same function that repeats itself. So if you keep going to another b up here, you keep going to a negative b over here, the same thing happens. You're going to get more positive, more negative, but the value, the absolute value, will be the same. Negative x, if you plug it into that tangent, it will be the same as if you were to throw the negative outside and just put the positive version of x in there. So a quick recap, we have cosine of negative x gives you cosine of x. The negative doesn't do anything. It's an even function. You can practically ignore the negative inside of your parentheses here when you're plugging in your angle for your cosine. But that's not true for your sine and your tangent. This negative, you're going to actually take it out. So if you have sine of a negative value, you can actually take out the negative and you just do negative sine of that positive value and negative tangent of that positive value. These are our odd trig functions. And this is what I would call your even odd identities. So I hope you were able to follow along with today's video and I hope you now know your basic trig identities. However, if you have any questions about what we saw today or even your own homework, you can always put in the comment box below or visit my Facebook page at Tutor Sempai and tell me all about it there. If you hadn't done so already, remember to leave that like. It surely helps the channel by letting YouTube know that you found the video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I'm really hoping to help with your homework, and I'm looking forward to seeing you again next week. I'm Courtney, this is your playlist, and this has been another session of Tutor Me Senpai.